All right. Thank you, Paul. And first of all, thank you very much to Jeremy and Rob for inviting me to this cool meeting. It's really, really exciting. I've been learning a lot, and I've also been reminded of that there's a lot to know. So to say. My background's in control theory. So many years ago, I was tenure track in a mathematics department, at applied mathematics department. But when I moved to Illinois, I swerved in a different direction. And so I think the talk will reflect that. It's kind of an engineering talk. And so most of my research career, I've been working on automated verification of dynamical systems using different types of methods. And kind of in the last 5-6 years, I've gotten interested in a little bit more informal methods and in particular model checking. And so that's what this talk is about this work, which has happened with a number of people over maybe the last 5 or 6 years. Okay, so I'm interested in sort of so the title says hybrid systems. So these are systems with sort of discrete and continuous states. I'll say a little bit more about this in a second. But really, I'm interested in the applications of these in sort of the cyberphysical domain. So I'll give some more examples in a minute. But the general idea here is that we have physical dynamics from sort of classical physics, or not necessarily only classical physics, but continuous sort of states that evolve on the continuum, let's say with the differential equation, interacting with sort of a state transition system that is a discrete state, like an automaton, or in our case, this can be a Markov chain. Okay. So roughly we can think about, and I'm so interested in composing these kinds of systems and seeing how they interact. And so roughly, sort of abstractly, you can think about them as physical processes that are interacting here, discrete systems like software or computers or what have you here. Maybe they have links between them. Okay, so I'll come back to this, but just to kind of say the type of model that I'll be devoting a good part of the talk to, which is our notion of a stochastic hybrid system. So we're going to have sort of two important variables here. One is Q, which is the discrete state, and we're going to assume Q is, for the most part, finite. So you can think about it as sort of the points, the nodes on a graph, or the states of a Markov chain. And X is a vector. It's a continuous state. Okay, so a solution to a differential equation. And the way we're thinking about this is, so this function, the way this thing evolves depends on both Q and X. So you have a differential equation that's evolving here on some state space. And at every point in time, it could possibly jump spontaneously to another state. Or this could kind of continue on its happy way, and maybe if it hits some boundary in this state space, it's forced to jump. Okay, so this kind of so this so this stochastic differential equation is driven by noise here, and notice these functions g and f, depend on these two things. Okay, so the state transition system's kind of hidden. It can spontaneously jump here, or it can be forced to jump when a certain condition is met by the continuous state. Okay, so I just wanted to start by saying sort of what sort of systems I'm kind of interested in. I thought it'd be kind of might be of interest to other people, to see some sort of real cyberphysical systems, some of these systems. So let me just kind of go through a few systems that I work with and that I'm interested in. And so in general, we're thinking about, let's say, robots or other types of autonomous systems that kind of interact through software, through communications, through wireline, through wireless, and we're interested in sort of software for these systems, and we'd like everything to work. Okay? So the idea, I think this general problem to be able to verify these kinds of systems is a super important sort of societal problem. And I think the sorts of methods that are being discussed in this meeting are the methods to kind of make all this happen. Yeah, so let me just kind of continue. So one thing that we're interested in is, of course, self-driving cars. Here's a new one we have at Illinois, taking delivery. So this is like a super important one to be able to verify. Here's a pretty cool legged robot. I realize I'm here at SAMU that a colleague of mine built. And so this is another example of these kind of systems where the dynamics have uncertainty, the dynamics are nonlinear, the software is pretty complicated. How do you go about being able to verify in some sense that something like this is going to behave in a predictable way, right? We've all seen like videos, and I think we saw some yesterday, of when they don't behave predictably. Of course, you can never model everything. You can never get everything right. I'm interested in sort of proofs within a formal system. I think sort of the methods that we're developing are trying to kind of make the gap from what you can prove formally to sort of taking that sort of jump that sort of engineering has to do right to the real thing to make that gap as small as possible. That's kind of what we do. Okay. Here's an extremely cool thing that we're just starting to work with at Illinois. This is like a solar plane. It can stay up 24/7. Another colleague of mine, Marco Kokomo's put this together. It's nice to be back in Pittsburgh. I used to live here. And this gives a nice sort of picture of what it looks like in Illinois. Our landscape's very flat. I've noticed a lot of hills in Pittsburgh since I arrived. So another system that we've been involved with, my students have at least, is Kiva Systems. This is a distributed fulfillment system. These are these robots that run the Amazon warehouses, and so they're running warehouses with now over 1,000, if not several thousand, of these robots in here. So Kiva was acquired by 6 years ago by Amazon. So this is kind of another interesting example. Here's some sort of kind of cute UAVs that I have in my lab. These are called crazy flies. It's a US quarter here. You can see they're very small. So we're interested in sort of swarm dynamics and flying these. And there's a little chip on here. This is called a decawave chip. And this is an ultra-wideband chip. So one of the other things I'm interested in is sort of the infrastructure that runs things indoors and outdoors. And so these UWB chips, for those of you who don't know that much about robotics, when you see things inside, typically people use infrared cameras to localize inside. These are systems that cost like $100,000 to outfit a room like this. We've been using UWB, which basically allows these things to chirp to each other and figure out if you hear a chirp from someone, you know that that he or she's on a sphere of a certain radius. You intersect a few of these spheres, and then you know where you are. So this is a technology we've been using for about 4 or 5 years now. And anybody who follows Apple will know Apple announced about a month ago that these chips are going on all their new phones. Not exactly this chip, but this technology, I should say. And so who knows what's to come. Okay, so I'll just tell you. So I have crazy flies. I also have some sort of in-house built hovercraft, and well, we're funded by this conference is funded by, or this meeting is funded by the Air Force, and funded by the Air Force for a long time. I used to call these aerial 2D aerial vehicles. So that's why I have them. But I wanted to kind of give another feel, a little bit of feel for some of the types of problems that we're interested in. So I'll just talk about a pursuer evador type problem. And so this is kind of like a game where I have a defender and I have an attacker. And I sort of want, the defender wants to, keep the attacker from reaching some goal, let's say at the end of a harbor. So, so you can set this up as a game, and sort of a mathematical game, and prove theorems about it. So this is kind of one thing we like to do. In the lab, then you can take a slightly more complex model and kind of do a simulation of something like the hovercraft, and maybe somebody has a joystick and it's like kind of like a video game. And then you can kind of bring it into the lab, and you can actually have the two hovercraft sitting there, and have a graduate student on one joystick, and then the other one is automated. Now, I'm doing this just for two players, but you can have as many agents as you want in this type of game. So then you kind of have a little bit more confidence, but this is all coming from something that you mathematically proved for a simpler case. And then you can actually put it on like real ships, right? And which is one of my graduate students who did this. Is a 100-foot ship in Chesapeake Bay at the Naval Academy. He runs an autonomy group now at NVIDIA. And I mean, like, it's pretty easy to go from like a theorem on paper in your office through these different steps using these things. And this is the coolest part, I think, is, at least for me, this is like Google Maps, and this is like the GPS data. You can actually plot what happened and sort of like the game theory formulation that you did. I mean, actually shows what the ships were doing, what the officer, here the intruder was an officer driving a ship. Obviously, we only did two. Here, the officer did a 360 with one of those ships to try to evade it, and you can see the defender kind of keeps the player in front of him. Yeah, and I think there are some people here who are interested in sort of implementation and so on. This was amazing to me when we did this. It was just done on laptops, plugged into your cell phones, and you can do everything. You can get all the sensing from your phones. And for education, I think if everybody's doing any applied courses, this is unbelievable. Use mobile MATLAB, and they tested it, around town in their cars before they did it. It's like for CS, somebody who's good at CS coding, this is like a one-day job almost, right? So if anyone's interested. Okay, so that's kind of, so those are some sort of like physical platforms. We're also interested in software too, and developing software tool or software tools in the sense of sort of methods to do programming rather than right now I'm talking about things that you would implement rather than tools to do verification. And so one viewpoint we have is we'd like to sort of get this sort of autonomy, autonomous agents. We'd like to get this paradigm of sort of an autonomous cloud or robotic cloud. I call it the Cyberphysical Systems cloud, where you have all these different agents hanging out here. And on the fly, they can sort of meet each other or query who's out there and then connect on the fly to each other to do sort of interesting applications. So in order to sort of enable that, a student a few years ago developed a service discovery module. He's at Intel now. And the idea here was that robots or other autonomous agents could kind of register with the system. And then if they wanted, if you're a robot that's, ground-based and you're walking around here, and then you'd like to get like an aerial view of something, you could query the network and say, is there any UAV out there that has a high-fidelity sensor that can tell me what's going on around me? You want to be able to do this just like we do sort of regular programming sort of without physical systems. So he developed something like that called Directory D. You can run it in a peer-to-peer method. The code's available online on GitHub. Or you can run it in sort of a centralized sort of database way as well. So we're interested in these kinds of tools. Yeah, and at least one startup is using it a little bit, but I shouldn't even put this on here because I don't know what the status is. So, okay, so, and then another thing we've been recently doing, this is with Cheyenne Mitra at Illinois, is we've been trying to, he has a grad student who's been developing a language to a high-level sort of sophisticated language so that you can program agents easily. Sort of like a modern language where like a lot of the details are hidden, sort of very abstracted language. And here we have some little cars and some UAVs that are kind of doing trying to service a bunch of points in a coordinated way. And you can write sort of programs in a very sort of efficient language to do this. It's called Cohort, and the grad student is Cheyenne who's been doing it. The way it connects to, I think, this conference too, is this language is, the way they've set it up is specifically so that by design it can be easily verified. Okay, so the language plugs into formal verification tools directly, Okay, so I think this is kind of like an interesting, for these types of hybrid models in cyber-physical systems, it's kind of an interesting area. Okay. Okay, so that's so the beginning part of the talk. So let me then talk a little bit more analytically then. And so this is the rest of the talk. Part one was kind of motivation and a little bit on systems. So here's what I'm going to talk about. I'm going to talk about sort of a framework for doing verification of hybrid systems, the types of models I talked about. A little bit about probabilistic model checking and a new tool that we have that's just come out. These are kind of not in order. And I'm going to talk a little bit about stochastic simulation. Our model checker uses something called antithetic sampling, or actually stratified sampling. I'm going to talk a little bit about that. I think it's kind of a cool idea, and I think one of the first, not the first to use it in this model checking framework. So this would be like a little bit of probability, but baby probability. So, and then I have a lot of slides. If time permits, I'll talk a little bit about X-armed bandits. So this is some multi-armed bandits. Many of you may be familiar with. This is kind of like a paradigm for learning. We've been trying to use this sort of stylized problem in the context of learning for these types of hybrid systems. And X-armed here means you go from multi-armed, which is a finite number, to the continuum. Okay. All right. So what we're interested in then is looking at the kinds of models I just described, but where we're going to have kind of a more sophisticated type of CS type specification, where like we'd have liveness, or something can't happen before something else can happen. In the past, what I worked on was sort of more traditional control performance metrics, which are kind of set up like in a Hilbert space with sort of an L2 induced norm, or some type of L2 into some sort of metric or sort of functional norm, if you like, to define the the performance. Here we're interested in putting like some sort of logical specification on the system. Okay. So then again, just to remind folks, just at a high level, this is again the model. Q is the discrete state, X is the continuous state, and yeah, and then so this is a system that's driven by noise. Okay. Okay, so just the big picture in terms of what we're doing. So you can think about sort of analytical models. Typically, if you're modeling physical systems, you'll have a PDE or an ODE or something like that. And sort of on the discrete side of the house, you have some type of state transition system. There's lots of different models for that, maybe not quite as standardized as on the physical side. And the problem is that these are kind of like in different domains. They're truly hybrid, and what you find is a lot of times is when folks work on hybrid systems, they're like experts on discrete systems. So the continuous dynamics are trivial, right? Or I mean, it's a word we all try to avoid, right? Trivial, but they're like very simple if you're kind of on the physical side of the house. And then if you know about this side, then this is very simple, right? And neither of them, neither is kind of satisfactory. So when we started this project, our view was, how do we deal with this? So if you go to most of the people in my department who are like experts on sort of simulating, highly nonlinear PDEs and so on, I mean, the first thing they do is discretize everything, right? I mean, they don't, there's no hope of getting an analytical solution for these things. So they discretize, but do it in a smart way. So our paradigm was kind of to try to discretize this and then get sort of something that's purely a discrete system, and indeed what we're getting is a continuous time Markov chain, and then do verification on that. And just going on the right-hand side here, here's the Markov chain, and then we'd like to do, and so the idea is that we'd like to do probabilistic model checking on this beast. But the important part is you don't want to just approximate. You want whatever theorem you can prove down here about this discretized approximate system, you want it to be able to say something strongly about this hybrid system up here, okay? So you don't want to just go down here and say, yeah, you know, if I discretize well enough, everything will be fine. You want sort of an implication arrow about a property of your original system that's not reduced. Okay, so let me just, there's lots of people who are like experts on this, I'm sure. I know. Let me just quickly say, so model checking, in general, you have sort of a discrete transition system of some sort. You have some sort of specification. The model checker kind of exhaustively, in some smart way, goes through all the trajectories and tells you, yeah, everything's fine, or, there's an error and here's the issue. In probabilistic model checking, you can think about this being now a Markov chain, right? But now you have a probabilistic spec rather than sort of just this, a logical spec that either holds or doesn't. Now you have a kind of logical spec that you'd like to hold with some probability, okay? And here, the model checker could say it's okay. It could say you're close, or it could say there's a problem. Okay? I won't say too much about this except for that. So one of the nice things is rather than having like a 0, 1 answer, yes, no, there's kind of a continuum, right, between 0 and 1, whether or not something holds with probability, like, the probability can be the continuum. So these kind of model checking methods fit into two broad classes. One is exact methods, where you actually like prove, yes, it is definitely holds with probability less than a certain amount. Another one is statistical, where we're doing simulation, okay, where you sort of like run simulations and you have some sort of mathematics to back you up that some statistics that back up sort of a hypothesis that you're making. So again, the big picture for us is goes like this. We start with a hybrid system with some sort of a logical spec. I'll tell you the logic we're using in a second. We do reduction to a continuous time Markov chain. We have to sort of get a commensurate or associated formula. We have to reduce the formula in some way. And then we do statistical model checking. Okay. So again, here's the original model. So the logic we're using is called metric interval temporal logic, which is kind of a generalization of linear temporal logic, so that you can make statements about functions that have a continuous variable, and you can talk about expectations. Okay, so you can talk about inequalities like this. I don't think we want to spend too much time on the semantics and so on. The kind of cool one is I think is this one, which is some condition holds on some time interval until a second condition is satisfied. Okay, and you can see it's written out here in general. And so this is kind of a trivial example. We'll come back to is the word trivial again. Yeah, sorry. So here's an example. Let's say we take some set in Euclidean space, and let's let C be the characteristic function here of this. Okay, and here this is not dependent on Q. Then this statement here means that so it's true on 0 to 1. The expected value of this is greater than a half. Means that somewhere on the time interval there's a time such that being in this set has probability greater than a half. Okay, so the reduction. Obviously this is not quite detailed or enough, or I'm going quickly. But the basic idea is we use an idea called the Maury-Schwanzig decomposition, which comes from statistical physics. And the idea is if you have a partition, sort of a finite partition of your state space, so you've kind of divided it up, the continuous part, into a bunch of distinct sets. If you use this particular decomposition, it tells you how to project everything down to a finite state space, and allows you to kind of keep track of the error between. So it gives you control of the error term essentially, going from the continuous dynamics down to this discrete this discrete state space now, okay, which is just a graph. Okay, so if we okay, so here's kind of the main result, and it's a theorem. So we have to assume something called gamma contractivity for our original hybrid system. It's kind of a technical condition, and it's not quite as strong as pure stability, but it's a type of this. So it puts some restriction on the kind of dynamics that we can have. But it says, providing we have this, if we verify the continuous time Markov chain, this sort of reduced system, with this extra, so I want to with this extra fudge factor here, which is delta over gamma, then so if this inequality holds for the reduced system, then this weaker inequality holds for the original hybrid system. Okay, so so this is the main theorem. So this is the arrow, this implication arrow I was talking about on an earlier slide. Okay, so we can do the reduction. We get something down to a finite dimensional Markov chain with a logical specification on it. You can do verification on that. If things hold, then it holds for the original system. Okay, and delta here is computed as an integral, and is something you can compute. And so yeah. So I'll just say something, because I sometimes have questions about this. Computing an integral, actually truly computing an integral in higher dimensions is like an extremely hard problem, right, in itself. If it's like R10 or something. So two things: if this happened to be, if you happen to luck out, and this is like a polynomial vector field or something, then you can explicitly do the integration. If not, then what does everybody do when they have a high dimensional integral? You have to do sampling, right? And this is kind of, you'll see, fits well with what we've talked about before. Okay, so then, so just to kind of connect the main result then to the simple example I stated before, if you wanted to verify the statement about the hybrid system, then it would suffice to verify this inequality for the finite Markov chain. Okay, with this little factor.
Are those factors that you can calculate, particularly calculate them?
Oh yeah. So good question. So I think I wasn't totally clear. So this thing that you'd like to calculate, yes, you can calculate this explicitly in cases where, for example, this is like, these are elementary functions or something like that. In most cases, you could, but even if they're not, you can do sampling. Okay, and then we'll see the answer we're going to get with statistical model checking is a sampling type answer. So these are well along. And I can say more on it in a second, but not that much more. Okay, so we've done the reduction. We have a theorem that says, if we check this, then everything's cool. Okay, so Nima Rui, who was one of the students who's working on this, developed a model checking algorithm for the kind of specs we have, and so let me just say, you give it a number of parameters, which are the system and some sort of spec, and then two parameters, alpha and gamma. And so the model checking algorithm says this: the chance of having a false negative is from this algorithm is less than alpha. The chance of having a false positive is less than alpha. So you can crank that alpha down as small as you want, but the algorithm could come back and say, I don't know. Okay, so you would like this to be small as well. So the algorithm's always good on this, but the tricky part is we need something called delta robustness in order to have the chance of it coming back with an unknown answer, saying I don't know. It's a little bit of a trickier thing to check, and what delta robustness is kind of a tricky condition. More or less, it sort of says if I wiggle and I'm not going to give a precise thing, but our papers have a precise definition. If I wiggle the trajectory a little bit, the answer doesn't change by much. Okay, so it's the kind of thing people will be familiar with before. So on the engineering side of the house, folks would say, if you can't wiggle it at all, then there's a problem with the system. You should go back to redesign, but that's not very satisfactory, right? So, okay, so that's it for our results. Just on the pure checking. So one of the things we applied this to was a Toyota benchmark problem, and I don't know if people remember. Well, I probably shouldn't bring this up, but I don't know why Toyota chose this problem, but it's a great problem. It's a accelerator problem, and basically it's a challenge problem that was set to the.
What are you not supposed to bring up?
Oh no, I'll tell you later. Yeah. So this is a powertrain problem, and basically what they want to do is I'll give it more explicitly in a second. It's basically checking that the powertrain and gear switching, acceleration, and so on functions as it's supposed to. Yeah. Okay. So and so this is a challenge problem. These slides don't really try to read them. These are meant to be sort of like not quite Rorschach's, but kind of like this big picture here. The big picture here is we have 4 discrete states: startup mode, normal mode, when somebody calls for power, and there's a sensor failure. Okay. The dynamics are some of the dynamics here are nonlinear but pretty simple. In other plants here, just means a system model. In other places, the model's kind of complicated or kind of like a horrible thing to deal with in many ways. You've got a sort of a non-polynomial ODE. It's like a delay differential equation, but kind of a simple one. It uses lookup tables. So that means you don't have sort of a symbolic representation of the function. You actually have to go like load data to find out what the function is. Or there just might be a program that does it. Again, let me just sort of give the big picture on what the specifications were here. So mu here is a throttle variable. It's a continuous variable. And basically what they ask for is at all times that basically the throttle not be more than 5% different from what the user is commanding. And then they ask that if you go from accelerating back down to normal, or normal up to accelerating, that again this sort of overshoot variable kind of settles down to a reasonable level. So your engine's not going crazy, or at least after a certain amount of time, it's satisfying this inequality. Okay, so it's called overshoot. The overshoot is less than a certain amount. Okay, and so what we checked was what NEMA checked was that the model satisfies the requirements with probability 98%. So that was a specification that this sort of sentence. The sentence holds with 98% probability, and our error probability, that alpha in this case, was 1%. Okay, and this was pretty efficiently solved. And at the time that we did it, which is probably about 3 years ago now, I don't believe any other group could do this verification with any method, probabilistic or non-deterministic. So we were kind of happy with that at the time. I don't know what the state of this is now. Okay, so there's an example, kind of like on a real on a real model that people use. I talked a little bit about the theory. We've been developing like general tools. We've been developing general tools to model check this, and we've been using this method I talked about, which is antithetic, which is negatively correlated sampling. So let me just tell you a little bit about this. This is kind of a little bit standalone. So if anybody tuned out, this might or may not be of interest. We have an independent interest in especially my colleague Matt West, in large-scale Markov chain simulation. Okay, so again, just a little bit of a big picture, and then I'll actually do a little bit of, almost like a little baby sort of math. So here's the question. I have some sort of a stochastic process, and so this is the distribution of the initial condition. And what you typically like to do when you study a process is you'd like to propagate this distribution forward, right, through the nonlinear dynamics, right? No hope of doing that analytically, right? No way, right? In particular, what we'd like to do is just keep track of the mean going forward, okay? So what people do is, folks be familiar with the sort of Monte Carlo method, right? Is what they do is they sample, and they sample from the distribution here, the initial condition, and then they propagate all these particles forward through the dynamics of the differential equation, and they kind of regard this as an empirical distribution, okay? And so usually the way you do this is you IID sample these. By IID, I mean you just draw fairly each time from the distribution. So basically what our method does is it doesn't do that. What it does is it correlates these, when you draw these, it correlates them in pairs, or in the stratification case, you can correlate them in more than pairs. And I'll explain in a second. Each one of these draws is still a fair draw, but you can get it so that they cluster more tightly around the mean, and we've been able to get 2 to 3 orders of magnitude speed up general Markov chain doing this. Okay, and you can do the same thing for particle filtering, where every once in a while you get some sort of observation of what the partial observation of the state. Okay, so just very simply then, if I have some sort of statistic or some sort of estimator of the mean, and I ask, so delta is sort of some estimate for the mean of the distribution, I ask, well, what's this error here? It splits up into 2 parts, right? One is sort of this error that depends on variance, or covariance. And the other one is bias error, like how far am I from the real mean? Okay, so usually we want this to be 0, and the sort of methods we're using are trying to push that baby down. Okay. Okay, so let me just explain the idea, and if you just listen to this idea, you'll get the whole thing. Okay. I mean, there's a lot of work still to do, but I mean, this is like sort of revealing. So take a Poisson distribution, and then plot the CMF, right? So if I go, if I say 12 here, it's means the probability of drawing from the distribution, and seeing something less than 12 is 0.75, and so on. So a standard way to given a distribution to draw from it, right, is to plot this guy and just do a uniform draw on 0 to 1, and then map back through here. So here I've chosen, maybe I get this number, and then I map back through this function and down here, and then that's a fair draw, right? And I could keep doing that. So with antithetic sampling, this is like a classical idea. What you do is you do your first sample, but instead of drawing again just on 0 to 1, instead you choose the point 1 minus your original draw. Okay? So notice that this is random, and this is like a random fair draw too, but they're definitely correlated. Now the coolness in this is, or to the extent that there's coolness, I think it's cool, is notice this guy comes down on this side of the mean. This guy comes down on the other side of the mean. So if I take the average of these, you have a much better chance of being close to the mean if you're on both sides, right? The other way you can end up with 2 on the same side. Okay. If you look at just two random variables and you take their variance and you write it out, you get the variance of the individual terms and you get this covariance term. Okay. So the key is obvious, you can't do anything about these two, but if you can make this as negative as possible, you can cut down that term I talked about, okay? And so antithetic sampling does that, it makes that negative, okay? And here's what you see as the Poisson parameter, which defines the distribution gets big. You can see, this is the variance of that you get. You see that this wins big. Okay, and this is like a little bit unfair because Poisson distribution basically becomes normal as that gets large. Okay, so here's the other one, and this is the one that we're primarily using in our model checker. is called stratified sampling. So instead of just doing 1 minus, instead what you do is you cut, or you partition the unit interval into strips, okay? And you sample from the first strip, the second strip, the third strip, the fourth strip, independently, but the samples are guaranteed to be in there each time you do it. And, the same trick works, right? You can see we had proof by pictures, here's a proof by picture, right? It kind of seems like it should work, right? Okay, so that's just for random variables. This is very classic. What we've been doing is applying this to stochastic processes. In particular, we call them lattice continuous time Markov chains. And they're beasts of this form. So X is the state here. And Y here is a unit Poisson process, which basically is a Poisson variable. And then nu here is a vector that tells us when this guy fires, which state gets. I'll give an example in a second. Which state gets changed. Okay. So this is like a Poisson representation of a continuous time Markov chain. It looks very specialized. It's also called the time change representation. Sometimes also called the Kurtz representation of a Markov chain. For continuous time Markov chains, it's extremely general. Okay? And mostly we've been doing finite state, where X could only be from a finite set, but it pretty easily generalizes to sort of countable state Markov chains. And then I've heard it said that it goes beyond, but I really don't know. Okay, so this is pretty general setup. We've applied these stratified and antithetic sampling methods to this model. It's a very general model. We've looked at it for a number of different things: aerosol coagulation, HIV infection, gene, and my colleague Matt's looked at atmospheric models. So it's like very, very general. And I won't talk about the details of the model. And how much time do I have, Paul?
5 minutes.
5? Only 5? Okay. Okay. All right. Okay. I'm going to turn on the jets here. Okay. So if you take that original model that I had, it's a little bit like unwieldy. And so a standard way to do simulation of continuous time Markov chains is to do the so-called tau leaping approximation. That's kind of a fancy word for basically doing like quadrature approximation of the integrals, okay? And then you get a discrete time a Markov chain where still this is a Poisson variable. So again, I'm gonna really have to speed up a little bit, but I'll just give you the ideas. So we've generalized this idea of antithetic sampling to this kind of a model. The algorithm parallelizes very nicely. All you need to do is be careful about how you seed the random number generator to do this, okay? And this is just a model of, like, this is the actual mean, and the dashed one is the antithetic sampled one. You can see the one that's more wiggly is the Monte Carlo one. So we've parallelized this. We've written code that can run on like a supercomputer. We've done it on the Golub cluster at Illinois. Golub was a PhD student at Illinois, and a long time ago. And we've gone up to sort of 64 cores. So we've done the examples I talked about there. I think the punchline here is that for that type of model, we were getting 100 to 1,000 times speed up, okay? For like totally general Markov chain, and it's almost free, okay? So then we were kind of satisfied with the tau leaping approximation, doing the tau leaping approximation. So we went to see, could we do something exact, okay? So we went back to this guy. And then, so if you want to simulate a Poisson process, how do you do it? So if you, in continuous time, you could go up to some point 10, okay, and then you could draw from the Poisson random variable with parameter t, and it'll tell you how many events happened up to this point in time, okay? And how do you figure out where the other events are? Is you just uniformly sample between 0 and 10, and that tells you where the events happened, okay? So that's how you would do that. Okay, so I think that if I want to do everything exactly in continuous time, maybe what I could do is I could do this correlated, negatively correlated sampling on the endpoint here, and then maybe that would make make these two different paths, correlated, and it wouldn't have so much error. So if you do that, here's the Monte Carlo, the correlation between two independent Monte Carlo draws versus doing antithetic sampling, right? So it's big in the middle, but where the antithetic or the negatively correlated sampling at the end, it's small. Okay, so so everybody's going to say, well, if I want to push this down, what should I do? Everybody says, I think everybody would say, well, let's put two of those guys together, right? So you do that, and it looks great. It goes down, but it goes up a little bit at the end, right? If you can see, this wasn't a good choice here. It goes up a little bit. The red goes up a little bit at the end. So let's see if I keep going. Turns out that was important. If I put a lot of them together, you actually do worse. Okay. So it turns out that little bit was bad. So what can we do? So it turns out if you look at, if you look at the Poisson at some intermediate time, it turns out it's binomially distributed at any intermediate time. So we use this property, and we do too. We take some points here, but we do antithetic sampling using that binomial distribution. Along this axis. Okay, I'm almost there. Okay, be worth it. So if you do that, here we've done use the binomial thing. We've done antithetic sampling using binomial theorem in the middle, and you can see it matches. And look, it doesn't go up at the end. And if you can concatenate a lot of these, it looks pretty good, right? You don't get this. You don't get it. You can't get it to come all the way down, but it's quite nice. Okay, so we've done similar relatively serious numerical experiments. It's not as good as with the tau leaping, but we're seeing more like 10 to 100 times speed up, and sometimes not speed up, and it's a little bit more complicated. The student who worked on this moved to Wall Street, so I don't know. I'm hoping we'll get some more results, but I'm not sure. Okay, so we applied it to particle filtering, and we have a paper on that. We applied it to some control, but most importantly for this conference is we have a newly minted statistical model checker that uses these methods. Yesterday when the other speaker, Sean Gal, was speaking, I realized that the student who'd worked on this and was a student on this project was his postdoc now. So, but I hadn't realized that, but he did a great job putting this together. So these are just graphics, right? Here's uniform sampling of the square if you don't do any negative correlation, and here's what it looks like if you do negative correlation. It's to me it's weird to other people who do work in this area a lot. It's not this looks like it should be the uniform one, right? But this seems more uniform. Okay, so he did he mostly did this through Prism, but you looked at some other model checkers too and compared ours using these methods, and it compared very well. And in a lot of cases, some of the other checkers, didn't survive. They didn't converge. Because we had pretty good performance. These are low. Here are some other checkers that ran out of memory, and it seemed like stratified worked the best. Antithetic worked well in some cases, but not uniformly. So so this is available. It's a usable tool you can download. For model checking. This is continuous time Markov chains with these kind of logical specs. Okay, and again, there's a little bit more math to go with this in terms of how to do. We used PCTL here. There's a little bit more math to kind of get the negative correlation, but folks could look at the paper for that. And I think I'm out of time, right? So I'll. No, I'm not gonna be that lame, but I'm just gonna end with just a picture of the multi-armed bandits, and that's for maybe another time. Yeah. So thank you so much. Yeah. Yeah.
At some point when you introduced the logic in MITL, you mentioned that it's sizable extension of underfield field. So what exactly is sizable?
Yeah, so this would be a better question for my collaborator. I'm not sure about the details of the decidability. We've on precisely this type of logic. So I just want to leave it there. Yeah. Sorry about that. Yeah. Yeah.
So in formal verification, there's always a mix of techniques. So with model checking and interaction, some things are fully automatic and some things. So you focus mostly on the automatic methods. But it occurs to me that one possibility is like you might have a situation where you have a model that's really not in the form that your model checker can handle it, but maybe with some kind of transformations, it is of that form. Can you see like a role for interactive theorem provers to sort of manipulate models?
Yeah, so I can. I think that's really interesting. And just to be really frank, coming to this meeting, that's one of the things I learned. I understand the whole program now of trying to, try to formalize things so that when things are equivalent, they are, right? So yeah, I think this could be a tremendous area. And like I started my talk today, I think that with saying that I think the methods that are being developed by this community could be extremely helpful and very, very complementary. And I think they're great opportunities, when I started out in control, I don't want to bore people, but I started in control, there was a super close interaction between sort of operator theory in pure mathematics and in control. So, my hope is that something like that could happen again, but yeah.
So, in model checking, my understanding is you always hit some state explosion problem when the system gets too big. And especially when you want to verify a system that has a parameter in it that is arbitrarily big. So, for instance, you show drones. If you have n drones where you don't know what n is, can you prove using your technology that the system still will behave well, or are you limited to a fixed finite n to be able to run it through this?
I think just in general, in sort of with discrete models, the difference between having something that could have, as long as you have an upper bound, I think you're okay. Okay, so if I so in theory, so to speak, if you say fewer than 1 million drones, that should be good for the theory. Of course, in practice, that's different. But I think the theory falls down if you have to have a counter. Okay, so you can't just have it be some unknown integer. And I think that's standard in I think this sort of an area. Going from an automaton to a counter is a big jump. Yeah.
That's the theory, but I mean just really doing the whole whole spec and model checks.
Yeah. So the thing I would say is.
How many drones can you handle?
Well, I don't know the answer to that, but that's something we're working on right now, right? I gave you the example of the Toyota powertrain problem, which at that time no one else had verified, and whereas our methods kind of scaled well to do that. There's no way to get away from sort of this state explosion. I mean, in general, but the runs that I showed, just now, where we'd benchmarked against standard examples and so on. I think we were pretty happy with the results, right? So we haven't solved everything, and I think there's a long way to go. But these are great. That's a great question, and the important question. That's what we care about, though, is trying to be able to verify, real systems.
Well, I've seen movies of those huge swarms of drones, so that I think runners of drones.
Yeah, you're definitely gambling. Yeah. So, okay.
Thank you.
Okay, let's put them in now. Thanks very much.
Okay, thank you.
So maybe we should push the schedule back 5